to the 3-6 notes for Calculus 1. In this section, we're going to take a brief hiatus at looking at formulas and rules for derivatives, and more go into the application side of things with derivatives. If you remember from section 2.1, we had some chat, basically a look at the concept of velocity. And if you recall, we actually learned about two types of velocities. So let's sort of summarize that. So it says, the average velocity represented the slope of the secant line through 2 points on your position function. So remember, the position function was always represented by the variable s, right? And average velocity was the slope of the secant line that we computed. We also took the slope of the tangent line out of a point of interest on the position function, and that was expressed as the limit of the secant lines, which was called the instantaneous velocity. So FYI, this entire section is based on instantaneous velocity. That's what we're going to focus on. So even though we're going to refer to velocity, just the word velocity, several times, when we say that, we mean instantaneous velocity. That's going to be the key of the section. Okay, so since section 2.1, we actually learned another helpful piece of information, specifically that the slope of a tangent line is actually called the derivative. So what does that tell us? That tells us that our instantaneous velocity, which we will refer to as v, or v of t, velocity with respect to time, is actually going to be the derivative of the position function s of t, or the position with respect to time. So this is going to be sort of a big concept in this section, is that if you're given an original function, which is going to be s of t, if you take its derivative, you are going to get its velocity, and by velocity we mean instantaneous velocity. Now note, when we did this in 2.1, you didn't know what a derivative was. So in order to find all these things, we were using tables, and we were using limit definitions, all those things. Now we have a much clearer path to finding the instantaneous velocity, and that's using the derivative of the position function. So if you look down here, you'll see that it's a summary of what we know already. So if we want to find the instantaneous velocity, which we'll just call the velocity of a function, we have to take the derivative of position, s, with respect to time. Another way to write that is to say s prime of t. So normally, what do? We say something like, we'll have f prime of x or dy dx. These are all variations of the same thing. Now we actually have specific variables of importance that we need to be able to call on. So this is technically the proper way to write the velocity or find the velocity of a function. And then let's talk about here. It says, it turns out some other interesting relationships develop in this field of study, which is mostly physics, by the way, including a new concept called acceleration. All right. Well, what do we know about acceleration? Believe it or not, a very similar relationship. It turns out that the acceleration function with respect to t is always going to be equal to the derivative of velocity with respect to time, which we refer to as v prime of t. So what's interesting about that is if we start with the position function s, we take its derivative to get the velocity, but then we take the derivative of velocity to get to acceleration. That means if we want to go straight from position to acceleration, we would need to take the second derivative of position to get to acceleration. And I showed you this in one lesson before. This is the sort of the dd way of determining, or the proper way to write a second derivative, which would be the second derivative of position with respect to time. So even though there's a lot of variables going on here, and I'm trying to explain them the best I can, literally what you need to know in terms of a summary is that you have position, you have velocity, and you have acceleration. In order to get from position to velocity, you take the derivative. In order to get from velocity to acceleration, you take a derivative. If you want to go straight from position to acceleration, you take the second derivative, essentially. So that is a sort of a flow chart that you can kind of remember, but that's exactly what you need to do or know in terms of the beginning parts of this section. To me, these aren't really formulas. This is just a simple concept you have to be able to look at. Okay, so let's look at some observations about what's going on up here, and some of it will be sort of a repeat of what we said, but what I said before. But let's be clear. It says we know that instantaneous velocity is the derivative of the position function. Okay, so we got that. It says note that you usually are computing a velocity function. Okay, so by velocity function they mean this velocity function. Therefore, you're not necessarily going to get an integer result. So what do they mean by that? Well, normally when you say velocity, people will be like, oh, it's, 45 miles per hour. That's a velocity of some kind, right? So you'll go, well, that's a number. Well, for us, what we're going to end up with is we're going to end up with formulas like 5t minus 6 or 3t squared minus 2t or something like that. So they're going to be more about velocity functions that you're actually going to be working with. Next, it says when measuring velocity, we set a specific direction, usually up or right, either one, as positive. So, for example, let's say we're talking about throwing the rock straight up in the air. So we represented up as positive, which means any object moving in the opposite direction is going to be a negative velocity. So negative doesn't mean decreasing. Negative means going in the opposite direction. That is a little bit of a change for student understanding, but be aware that that is the case. Next thing. It says another concept called speed is the magnitude of the velocity, or in other words, the absolute value of the velocity. So let's say you have velocities of 10 miles per hour and negative 10 miles per hour. So 10 miles per hour would be in the positive direction, whatever that is set as, and negative 10 would be in the opposite direction in the same speed. Note that, like I just said, these two velocities are the same speed, but they're just in a different direction. Last thing, which is the new thing for us, it says similar to function to derivative relationship of position of velocity, acceleration is the derivative velocity, as spoken of already. Specifically, acceleration is the rate of change of velocity, or in other words, how fast the velocity is changing at a given moment in time. Note that if the acceleration is positive, the object is moving in the same direction as motion, and the object's velocity is increasing. If the object has a negative acceleration, the object is moving in the opposite direction of motion, which leads to decreasing velocity. Okay, so these are sort of concepts I find that students usually understand fully about, 2/3 to 3/4 of this, and the other part they have to really do a little bit more thinking about. But it is a lot less mathy. I like that word. It's not a word, but I like it. It's very less mathy and more conceptual. So obviously that can be a little bit of a struggle for some students. Really the best thing for us to do in this section, and the most important things for your exams, is to look at how these formulas are applied in a real world setting, also on exams, which is what most of you are most interested in, obviously, making sure that all is good. Now note, there are a lot of concepts on this page and in the following pages that some of them are challenging to really understand, so really make sure that you're with me and you study this well. Let's take a peek at number 1. It says, suppose the position in feet of an object moving horizontally. So we know that the object is moving horizontally. At time t is the following formula. So it says S equals, it should really be S of t if we want to be very technical, or in other words, position with respect to time is equal to this third degree polynomial for 0 to 4 seconds. So note It doesn't say 0 to 4 seconds, but we know that because t is time in seconds. So this only exists on that value. It says assume the positive values of s, so positive positions correspond to positions to the right of s equals 0. Okay, so that's not too important for what we're doing here because we're not going to be graphing it. So it says for letter A, it says determine and graph the velocity function on the interval 0 to 4. Okay, we'll start with that. Okay, just this. So if we have the position function, how do we find the velocity? Well, we go back to our formula over here. Let's get rid of all the noise here. So if we want to find the velocity of a function, we must take the derivative of the position function. So that's what we're going to do. So we're going to do s prime of t, which is f of t, is going to be equal to find the derivative of this value. So the 3 goes to the front, negative 18 t squared, 2 goes to the front, 72t, and anything times a variable is 54. So now the variable we're doing is t, but there's no difference between using t and x if that's the variable of importance. So right now this is the velocity function. Now it says graph it. Well, I did it for you over here. So this graph over here is actually the velocity function. So it's the versus time. This is going to be the velocity with respect to t. So, for example, if you look at any one of these numbers or values of the time, you can get an idea of where the velocity is actually going to fall. And that's where the next part comes in. It says also determine when the object is at rest, moving backward, and moving forward. Okay, so here's the key. We need to determine when this object is at rest. So what do we know about the object when it is at rest? What is its velocity? I'm sure most students right now are screaming in their brain, of course, the velocity would be 0 when it's at rest. So if I want to know when this is 0, then what do? Well, there's two options. I plug in 0 for t, or I set the whole equation equal to 0. Every instinct in your body should say to set the equation equal to 0 because I'm not asking for when the time is 0. I'm asking for when the velocity is 0. So I need to replace the velocity with 0 and solve this equation. Okay, so what are we in? We're in algebra world. Now it turns out that lucky enough, there's a GCF of negative 18 that we get out of this. So if we take out a negative 18, we get this, and if we factor, we're going to get t minus 3 and t minus 1. So what does that tell us? That means that this object is at rest at t equals 1 and t equals 3 seconds. So this is at rest. So let's look at our diagram. At t equals 1 and at t equals 3, what is the velocity? Well, the y-axis is the velocity. So or in other words, it's the v-axis here, but that is 0. So this checks out perfectly. But we have to determine so object at rest is really easy to find, but what about moving forward and backward? Okay, so we know that this object is moving forward if its velocity is positive. So remember what we set up here about velocity, measuring velocity, we set up a specific direction as positive. If any object is moving in that direction, the velocity is positive. If it's moving in the opposite direction, the velocity is negative. So forward is going to be positive in this scenario. So if you look at this graph, where is the velocity positive? It's any place over the t-axis, so to speak, or the typical x-axis. So on what interval does that span? It spans from 1 second to 3 seconds. So my question is, does it include 1 and 3 seconds? Hopefully you say no, because what do we know about this at 1 and 3 seconds? It's at rest. So it makes a lot of sense that if we're moving backward, that's occurring at any value that is below the axis. Therefore, any place where that happens. Well, remember, this entire thing starts at 0 seconds, right? So we don't really know what's happening at 0 seconds. So technically, if it's included, then we should say 0 is included. What is it going to but not including? It's going to be all of this right here. So it's going from 0 to 1 on the t-axis. It stops, becomes positive up here, the velocity, but then it becomes negative again anywhere from 3 to 4. We're going to include 4 only because it's included in this spectrum. So how do we put these together? With a union symbol. So pure interval notation we're returning to from old school algebra, pre-calculus, all the things that you've learned. So this is the graphical way to determine this setup, and this is something you're going to have to be able to do. So make sure you practice that for sure. There's a lot of other things to get to here in the other problems that we got going on. Okay, it says use your findings in A to find the displacement of the object over 4 seconds. Okay, look at the word they used. Displacement. So displacement has the word placement in it, which is synonymous to the concept of position. So when I ask for the displacement of the object, you shouldn't be going anywhere near velocity because it has nothing to do with it. We only care about the position of this object over the time span from 0 to 4. So how do we find the displacement of the object? Well, what we need to do is we need to take where the object is at, so real quick, where the object is at 4 seconds, and we need to subtract where the object is at 0 seconds. How do we do that? We do s of 4, which is plugging 4 into our position function, minus s of 0, which is plugging 0 into our position function. So this is a very algebraic concept for sure, but that is all you have to do in order to find displacement. So how do we do that? Well, we go back to our original function, and we're going to get negative 6 times 4 cubed plus 36 times 4 squared minus 54 times 4. Then we subtract the same values with 0 in them. Now, if you look at our function to begin with, you'll notice that there's no constant at the end of this sucker over here, which means when you plug 0 into this whole thing is just going to be 0, which means whatever we get for s of 4, which is the first part here, we're going to end up as our answer, essentially. So what are we going to get? We're going to get negative 24 minus 0, which is negative 24 feet as our displacement. So what does that mean in the scope of our problem? If you remember, this is an object moving horizontally. So if it's moving horizontally, it starts somewhere. So let's say it starts, I don't know, let's say this is your starting point. So if you move forward, you're moving in the positive direction, but then you could also move backwards in the negative direction more. So right now you would be, let's say, behind where you started. Well, that's what this means right here. So this object at 4 seconds is going to be 24 feet behind where it started. That is the key concept. It's not always easy. I usually use myself as a prop in class to sort of explain this a little bit easier because students have an easier time sort of seeing it. But literally, this is the best way to think about it. Let's say you're here. Let's say I decide I'm going to walk 10 feet forward, so plus 10. But then I go, you know what? I'm going to then, in the same thought, I'm going to go minus 15 feet on the same line backwards. So where am I displacement-wise from the beginning? I'm actually negative 5 displacement-wise from the beginning. That's kind of the concept, or exactly the concept of what we're actually looking at here. Okay, so let's go into displacement's good buddy, distance. Okay, two of the most confused concepts in sciences and in calculus is displacement and distance. So, and this is the example I used up here, right here, is going to help a lot. So if I ask for the displacement of myself after going forward 10 and behind 15, I get -5. But what is the total distance traveled in that scenario? That is 10 forward, 15 back. It's 25. No signage at all. What do we need to do? We essentially forget negatives and we just add the absolute value of each one of these and get 10 plus 15 is 25. So displacement and distance are different. So we need a way to be able to calculate that in a problem that is just like this without having to use props or, diagrams to do it. So what we were saying, well, first of all, it says, remember that finding the total distance requires knowing when the object is at rest. So in our example, the object is at rest right here, right? So I move forward, I'm at rest, I move back. So I use this as a way to separate my lengths so that I take the absolute value of each of these. So if you recall, we found that this object is at rest at 1 and 3 seconds. So that means we need to separate our interval into sort of divisions between 1 and 3 seconds. So what does that mean exactly? So the first length of time, I'm going from 0 to 1 second. Then I'm at rest. Then I'm going from 1 to 3 seconds, and I'm at rest. And then I'm going from 3 to 4 seconds. Those are my times. My times at rest are how they're split up. So I have 3 different values that I must calculate, or in other words, 3 different displacements that I must calculate. So what do? So how do I know where I am from 0 to 1 second? I have to do s of 1 minus s of 0. How do I know where I am from 1 to 3 seconds? I need to do s of 3 minus s of 1. How far do I need to, or what's the position difference between 3 and 4 seconds? S of 4 minus s of 3. So essentially you're computing the displacements, but you're being very careful not to overlap the rest values. You want this thing to be at rest at a certain point so that we're getting this full distance, then this full distance separated. If we don't do that, we will not get the correct response. So this is all basically computations. S of 1, we didn't calculate S of 1 yet, or S of 3. We know what S of 0 and 4 are. So let's do S of 1 and 3. So S of 1 is going to be, again, it's going to be -6, 1 cubed plus 36 times 1 minus 54 times 1. S of 3 is going to be -6 times 3 cubed plus 36 times 3 minus 54 times 3. I believe the middle term is squared, so I just have a little bit of a typo there. So when we calculate these, we're going to get specific values. So S of 1 in this is going to be -24 if you put this in the calculator. S of 3 is actually going to be, it looks like 0, interestingly enough. So if we put all of these values, so we got, this is -24 is S of 4, 0 is S of 0. So if we put all of these in as we have it, what are we going to get? So S of 1 is -24, and we are subtracting 0, which is S of 0. 1 to 3. So for S of 3, we're going to get 0. We are subtracting S of 1, which is -24. And for S of 4 minus S of 3, S of 4 here was -24, and we are subtracting S of 3, which is 0. So if we do the math, we are going to get the following. Okay, so these are the displacements that we actually followed. So if I was to do a diagram, this is what it would look like. So suppose we were at 0 seconds. From 0 to 1 seconds, just hold on 1 second. Let's do a different color. From 0 to 1 seconds, I go backwards 24, so -24, and I end up here. Then I take a rest. Then from there, I go back to positive 24, and where am I? I'm at my original position. From there, I go again negative 24, which is backwards to this spot. So in the end, if I was to do displacement, I would be at negative 24 essentially from my starting position. But I'm asking for total distance traveled. How do I find that total distance? I need the absolute value of these numbers. So I need to find the absolute value of, so I'm going to write total distance equals absolute value of 24 plus absolute value of 24 plus absolute value of negative 24 gets me 72 feet as my result. So I find that students sometimes struggle with this just because there's a lot going on, but hopefully the diagram helps a little bit. Now note, you're not, it's really hard for me to do this, right? It's hard for me to go, okay, we move this way, now we're moving back this way on top of it, so I'm moving back this way. I mean, you're not seeing anything, so I'm actually, making those lines staggered, but in reality, you're doing it on top of each other, going back and forth on the same path. So, but the key is that we have to use the where the object is at rest, what times, to split up these guys so that we can take the absolute value of each of those distances to get 72 feet for the distance. Okay, so let's talk about D. It says determine the acceleration function on the intervals 0 to 5. Okay, so what did you learn? You learned that acceleration is equal to the derivative of velocity. So how do we find the derivative of velocity? Well, we find our velocity equation, which is back here, right there. So how do we do that? We need to take the derivative of that function. So let me write it out. So we're taking the derivative with respect to not x, but t of negative 18 squared plus 72t minus 54, right? Okay, which is going to be negative 36t plus 72. So therefore, this is the acceleration function. So if you're looking for when the acceleration, what the acceleration is at a certain time, you use this function, just like you would use this function up here to find the velocity at a certain time. Well, guess what? That's the next question. They want to know what the velocity and acceleration of the object respectively are after 2 seconds. So we need v of 2 and we need a of 2. So what's v of 2? It's going to be negative 18 times 2 squared plus 72 times 2 minus 54, which is going to be 18 feet per second. So velocity is in, where is it? Feet per second. Remember, it's change of position over time. The acceleration now, we have a new formula. It's negative 36 times 2 plus 72, which is 0. Now note, what is the label or for acceleration? It's actually feet per second squared, but the square is in the denominator. That's something students mess up. They put the square in the numerator. Acceleration, it's feet per second squared, or square seconds. So we have 18 feet per second velocity and 0 acceleration at that point. That is our velocity and acceleration after 2 seconds. Okay, last question. It says, determine the acceleration of the object when the velocity is 0. Okay, so what happens usually when a student will read this problem, they'll just start like crashing their brains. So in reality, this is not meant to be a hard question. Why? Because I claim we've already determined when the velocity is 0, or in other words, when it's at rest. When is the velocity in this problem 0, or in other words, when is this object at rest? At what times? At 1 and 3 seconds. they want to know, therefore, what is the velocity at each one of these times. And that's all they're looking for. Negative 36 times 1 plus 72, and negative 36 times 3 plus 72. This is going to be positive 36 feet per second squared and negative 36 feet per second squared. These are our results. So you just have to be ready for pretty much anything in this section. It is a little bit of a challenge sometimes for students because there are a lot of very tiny individual concepts in here that you have to keep track of. Besides the typical velocity and acceleration, you need to know displacement, you need to know distance, and you want to talk about when an object is at rest, moving forward, backward. All of that is really something that could appear on an exam, so you have to be ready for it. Alright, so the one thing we didn't talk about was the relationship between velocity and acceleration. So what we're going to do, we're going to talk about the relationship between them when it comes to the concept of speed. We're going to do that only because that is what you guys are most familiar with when you're driving a car, is speed, essentially. So what's on the speedometer? I'm going to be chatting a lot, so you can see there's like paragraphs here going on, right? So we're going to be chatting this up. So not going to be writing a lot, but really open your brain up right now. Make sure it's clear, and you can understand what is coming from. This is important. It says a common question might be asked is when the speed of an object is increasing. So when the speed of an object is increasing, that is the key concept on this whole page. It is important for you to realize that this only occurs when velocity and acceleration have the same sign. Okay, so what does that mean? So if velocity and acceleration are either both positive or both negative, then the speed of the object is increasing. If the speed will not be increasing, if the velocity and acceleration have different signs, so one is positive and one is negative. That is the first very important concept to understand, which will help us do some of the problems before. Now, the first question I usually get is, why? Why is this the case? So, long ago I came up with this great example that most students completely understand once I read it, so just listen, basically. It says, it is pretty common, right here, it is pretty common knowledge that the acceleration due to gravity is 9.8 meters per second squared. In practice, though, since gravity is pulling downward, we often give it a negative value of negative 9.8 meters per second squared. Let's say we throw an object straight up in the air. Since the object is moving up, it is therefore progressing in a positive direction, and the velocity is considered positive. What do we logically already know about the speed of an object as it progresses towards its peak? Well, think about it. If we're throwing an object straight up in the air, what's going to happen to the speed as it keeps going? Is it going to increase or decrease? Well, I think most of you, after that first section, are going to tell me it's decreasing because, of course, gravity, right? So what's important? The important element here is that we have a positive velocity, it's going upwards, but a negative acceleration due to gravity. So therefore, since the sign is different between velocity and acceleration, this leads to a decreasing speed. So again, if you have opposite signs for velocity and acceleration, so remember we designated velocity up as positive, so that's how we started, but we knew that acceleration due to gravity is negative, so since these are conflicting, it leads to a decreasing speed. How about the other direction? So once the object reaches its peak at zero velocity, it starts falling downwards. This creates a sign change with our velocity, which is now negative. So we now have a negative velocity. But did the acceleration due to gravity change? Think about that for a second. Did it change? No, gravity is still negative 9.8 meters per second. It's a constant. So we still have an acceleration of gravity, which is negative. So look, velocity and acceleration have the same sign, which based on what this is, the velocity and acceleration have the same sign only when the speed is increasing. But what do we know about an object that's falling to Earth? Isn't it increasing in speed? It sure is. So this is absolutely the best example that I can give you to have you understand this. So hopefully that's settled right into your brain without any issues, because that's what you're going to be sort of looking at here, is that clearly, since velocity and acceleration have the same sign, when it's moving towards Earth, it's going to lead to an increasing speed. Okay, so it says, now let's return to the previous problem, number 1, and determine when the speed of the object is increasing. The most ideal way to determine this is to examine the velocity curve with the following in mind. Alright, so just as a reminder, this was the velocity curve, which was an upside-down parabola designated by this formula right here. Right? So this formula right here. It was this guy. So we have v of t graph versus time, and it's from 0 less than or equal to t less than or equal to 4. So 0 to 4 seconds. So what can we do? First bullet. The velocity is positive when the curve is above the x-axis and negative below the x-axis. So you can also say t-axis if you like, but we've already determined that we know that the velocity is positive above the axis and negative below the axis. But that is only for velocity. Okay, just for velocity. So technically, we can determine that right now. So let's do that. So remember, we're looking for our, where things were split up. So remember, this graph we split up from at 1 and 3. We're also going to split it up at 2, and I'll explain why in a second. So first of all, before 1 second, what's the velocity? The velocity is negative. So we're going to write v minus for everything from basically here to here, right? But I'm going to erase that because we're going to need it. Now, I'm also going to go from here to here. What is the velocity then? Is it positive or negative? Well, it's above the axis, so it's positive. What about here to here? Still above the axis, positive. What about down here? It is a negative velocity. So when we do these problems in the beginning here, we can clearly see where these velocities are going to be. So anywhere above is positive, anywhere below negative. Now, next part of this, it says recall that the acceleration is the derivative of velocity. What do you guys remember about derivatives? It is the slope of the tangent line. So, I know this is going to be really difficult for students, but this is a velocity curve. So if I wanted to know the acceleration at, let's say at 1 right now, right? At 1 second, I would draw the tangent line and I would find its slope. That slope is the acceleration at time equals 1. So a lot of students will be completely blown away by what I just said. But that is based on everything that you've learned so far. The curve itself is, the whole curve, upside down parabola, is velocity. But we don't have the acceleration. Technically, we have the formula. We found it over here, right? So it's a line, but if we want to examine acceleration just on this graph, then we need slopes in order to do that. So that's what we're going to do. So for example, let's say I made a random point. Actually, let's make it a different color, orange. And I drew a tangent line. Same thing here. Anywhere from below 1 second, I'm going to draw it. What do we know about all of those tangent lines? They create what type of slope? Positive or negative? Hopefully all of you are saying those are positive slopes. Well, those lines represent acceleration, which means our acceleration is positive anywhere before 1 second. Well, what if I did that again up here? What if I drew a tangent here and a tangent here? Again, what do we know about all of those Slopes, they are positive, so A is positive. Hopefully you see where this is going. Again, what if we went past 2 and we went to here or here and we drew slopes? Our tangents, their slopes are all negative. If I went here or here or here and drew tangents, those are all negative, so the accelerations are negative. So, let's go back and look at our analyzing bit here. Split at 1 and 3 seconds. So let's talk about our intervals and how they go, and then we'll make a judgment about our result. So where is the velocity increasing? It appears that it's increasing anywhere above the x-axis. So from here to here, it's increasing. So we would write between 1 and 3 seconds. Okay? Where is it decreasing? Anywhere before 1 or after 3. So we would say, again, to be specific here, we would say, if you recall, it included 0 and 4, so we would say 0, 1, union, 1, 2, or not 1. Anywhere to the right of 3 and before 1. So 3, 2, 4. Now note, if I want to be clear on this since we're doing it, if I didn't give you a limiter here, then you would be putting infinities here, negative infinity, infinity, and you wouldn't have square brackets. And if for some reason I had, let's say, put strictly less than instead of equal to, you would have parentheses there. What about acceleration? Well, it appears that this sucker is accelerating, is increasing all the way from here to 2. So we're going from 0 to 2, we are increasing acceleration. Remember that we're not, some students will be like, oh, don't you leave the number 1 out? Well, you don't, because we don't know what's happening right now at 1 other than the acceleration is positive. So if I draw like a tangent line at 1, I'm getting a positive slope that's going to be a number. I'm not getting 0. 0 is the velocity, not the acceleration, so be careful with that. So what about when the acceleration is decreasing? Well, that is occurring anywhere from 2 all the way to the right, which is from 2 to 4. Okay, so these are our intervals for increasing accelerations and velocities. So let's go to our last important concept. Get rid of this. It says, once you have the intervals of positivity and negativity for your velocity and acceleration, you can then determine when the signs are the same to identify increasing speed. Ta-da-da! Look at each one of our 4 regions that we have. So our first region is right here, right? That's our first region. It's from 0 to 1 second. Are the signs of velocity and acceleration different, or are they the same? They are different, which means the speed is definitely not increasing. It is decreasing on that spectrum. All right? Well, what about from 1 to 2? It appears that the signs are the same, which means that we know that this is increasing 1 to 2. Well, let's start looking at some other locations. What about from 2 to 3? Well, it looks like the signs are different, which means the speed is decreasing. And then what about from 3 to 4? Well, 3 to 4, the signs are the same. Therefore, that is another value, wrong thing here, another value of interval in which we are going to be having the speed increasing. So that is our interval. So it takes a while, obviously. It took a while to explain and go through, but this is a very basic, not basic, but typical example of a speed increasing problem. So I tend to lay off this on exams, but since this is online, anything could pop up on an exam. It's just what I have at my disposal. You'll probably get one in your homework, so be ready for that. Okay, so let's do one more example where we try to bring all of this together. Some of these will be a little very different because of the type of function that we're dealing with. But let's start. So suppose the position of a particle moving along a straight line is given by the function s equals t squared minus 6t. Again, ideal that this is s of t, so it's more of a function. Even though s is okay, this just gives us a better function look in seconds. Okay, so this is our position function. It says find the velocity and acceleration at time t. Okay, so when they say at time t, that means you're giving the function. You're not giving a number answer, you're just finding the function. So again, the velocity is equal to the derivative of position. So I need to find the derivative with respect to t of t squared minus 6t. Well, what is that equal to? It's 2t minus 6, which is going to be our velocity function. Acceleration. The acceleration is equal to the derivative of the velocity. So I'm taking the derivative with respect to time of 2t minus 6. So what's that going to be? That's going to be, interestingly enough, just the constant 2. So what does that mean? Our velocity function is 2t minus 6. We can find a variety of velocities by just plugging in the time in which it appears. Also note it's the graph of a line, which you see over here, v of t versus t. The acceleration, believe it or not, is constant. So this particle is moving at a constant acceleration the entire time. If we want to find the velocity and acceleration after 5 seconds, then all we have to do is just sub into the respective values. So we need to find v of 5, which is 2 times 5 minus 6, which is 4. We do need a label, so this time we have meters and we have seconds, so meters per second. And for a of 5, some students will get stuck here, but note there is no t to plug into. Why is that? Because it's constant no matter what t is, so the result is 2 meters per second squared. So if you want to make a note, constant here. So that would be the best thing sort of to look at in that standpoint. Okay, so going back to our problems before, if you want to do practice here, obviously you can stop at any time and try to do it yourself and check your work. That would be phenomenal. That means that you're ahead of the game and you're all over this. That would be really good for you in terms of understanding. You don't need to do that, but feel free to always pause the video and try to do it yourself. It says determine the object is at rest, moving forward, backward, and moving forward. Okay, so again, when is an object at rest? Whenever the velocity is 0. Okay, so look at the function up here, the velocity function. We want to know when this is 0. So 2t, so at rest, it's going to be 2t minus 6 equal to 0, which is going to give me a time, add 6, divide by 2 of, right, 2t equals 6, and then divide by 2, we're going to get t is equal to 3 seconds. Okay, just in case you didn't follow that. So if you look at the graph, you say, oh, yep, indeed, that's where we're going to cross the t axis, so we're going to get 3 seconds. So when are we moving forward? We're moving forward whenever we are above the graph. So where is that? That is from 3 on. We don't, in this problem, they don't specifically give you values. This over here should say from, so write this, 0 is less than or equal to t is less than or equal to 10. So let's use that. So from, it looks like we're moving forward whenever 2t minus 6 is greater than 0. So that's going to be from 3, for t greater than 3, which is going to be from 3 to 10. Let's do, you know what, for this one, let's do this just to do something different. So we're going to do from 3 to 10, and moving backward is going to be wherever 2t minus 6 is less than 0, which means t is less than 3, which is from 0 to 3. Note, we're not including 3 because it's at rest there. Okay, so these are the intervals for at rest, moving forward, and moving backward. Okay, so next, we need to find the total distance traveled. So not displacement, even though we need displacements in order to do that. Between rest times, we need the total distance. So again, we always need to identify when the object is at rest? Well, we determine that that is at rest at t equals 3 seconds, right? So what is our full spectrum on? It's from t is from 0 to 10. So what we need to do is we need to break this interval up and find displacements from 0 to 3 and 3 to 10. How do we do that? We do first s of 10 minus s of 3, and then we do s of 3 minus s of 0. Okay, so these are, to be clear, displacements, but we're going to get negative answers sometimes. It doesn't matter, because when we find the total distance later, we're going to be taking the absolute value of these scenarios. So what are we basically going to do here? We're going to find each one of these. So s, don't plug it into velocity. Plug it into t squared minus 6t. So remember, s of t is equal to 6, again, I just missed that. T squared minus 6t. Okay, so what are we doing? We're doing 10 squared minus 6 times 10 minus 3 squared minus 6 times 3 for our first value. For a second, we're going to do that same end value, which is 3 squared minus 6 times 3. And we're going to subtract 0 squared minus 6 times 0. Okay, so if we want to do a little bit of a shortcut action here, this value here is going to be, looks like it's going to be 40. This value here is going to be negative 9. This, again, is going to be negative 9. And then this is going to be 0. So over here, we're going to get 40 minus a negative 9, which is 49. And over here, we're going to get negative 9 minus 0, which is negative 9. Okay, so what do we need from this? Well, we need the total distance. Well, what is the total distance? It's the absolute value of the displacements. So it's going to be the absolute value of 49 plus the absolute value of negative 9, which is going to give you 58 meters as your total distance, 58 meters. So what is the most common mistake, by the way? So I didn't mention it earlier, is students will add these values as is, get whatever number it is. It looks like it might be 40, and then they'll take the absolute value of whatever that is, and that's your answer. That is the incorrect answer. Do not do that. You cannot do this any other way but set it up by dividing the time into pieces, find each displacement, take the absolute value of the displacements, and add them together. Okay, so last problem in this part, we need to determine the speed of the object, where it's increasing. That's it. So if you recall, this is from our previous page when we analyzed the velocity for V's and A's, right? So now we have a picture again, which we can do that for, which is over here. So what do? Again, velocity is always positive above the axis, negative below. So we already know that. So what do we need to do in terms of acceleration? We need to analyze the slope of the secant lines above and below the value 3. So if we go here, in time 3 seconds on, it looks like no matter where I draw a tangent line, the slope is always going to be positive because it's rising from left to right. Again, if I go before 3 seconds and I draw tangent lines, again, they're all rising. Well, we kind of knew that because this has a constant positive acceleration. So if we analyze where this could be increasing, it's wherever velocity and acceleration have the same sign. If you look here, they don't. If you look here, ta-da, they do, which means that this is increasing anywhere from 3 to 10. So believe it or not, this is just the answer, 3 to 10, with a little analyzing of accelerations and velocities. Okay, so this is kind of a completely different topic. So we're kind of like creating a break here. So no more velocity and acceleration. That is a physics application of calculus. Now we want to go into an economics or business application of calculus. As you see, this is a big application section. So this is something that you would learn if you were taking more detailed you would learn if you were taking a business calc class, but we touch on it briefly because it is important. Okay, so definition. There's two important things that you're going to need to know, and we'll talk about those. First, we define a cost function as capital C of X. This gives the cost to produce the first X items in a manufacturing process. So usually C of X is an equation. So for example here, it's a polynomial equation. So by plugging in a number there, we get the cost of the item for the first. So if you plug in 2, you would get the cost to produce the first 2 items in the manufacturing process by just evaluating that function at 2. Okay. So what are the important things beyond this you need to know? First, we have what's called the average cost function, which we represent as C bar. So if you guys took statistics, you would have learned that X bar is the sample mean or sample average. So it's the same concept. C bar represents the average cost function, and you get it by taking the cost function itself up here and dividing by X, which is the number of items in the manufacturing process. Now, when you're doing the problems themselves, you're usually just dividing by the variable X, but we will talk about that when we get to it. So the other concept is called the marginal cost. Now the marginal cost is defined as the approximate cost to produce one additional item after producing a number of items. So let's say I want to know what the marginal cost of 5 is. That would be the cost of producing the 6th item. So if I created one more item, how much would it cost? Now, a lot of you might be, well, doesn't it cost the same to produce items every single time? It actually doesn't. The cost to produce something in an assembly line, like an object or some type of item, actually fluctuates constantly. That's why students of economics and business must learn calculus, because they have to be able to understand that process, and that's how we know it. So believe it or not, the marginal cost is found by just finding the derivative of the function. Okay, the best way really to understand this is just to do examples, like most things, but really with this, because it's a foreign concept to pretty much everybody that takes calculus for the first time. Okay, so again, the cost of producing, this is a weird X, I don't know where this came from, it looks like stretchy X. The cost of producing X items is given by the function C of X equals this 2-degree polynomial. Okay, so it says determine the average cost function. So if we return to the average cost function, it's called C bar of X, and that is going to be equal to the cost function divided by X. So the cost function in this problem is 1,000 plus 100x minus 0.25x squared. And we need to divide this by x. How do we do that? We divide each value by x, as we can do with anything, any type of algebra problem. And then we simplify. So what do we get when we simplify? Well, we can't simplify the first thing. We can simplify the next by crossing out the x's. Okay, we can simplify this x and this 2 to make it a 1 and get minus 0.25x. So this is the average cost function. So if I want to know the average cost of producing a certain amount of items, all I would have to do is plug in a number into this function in order to find it. If I want to know the total cost, I plug it into this guy up here. So here we go. B, it says determine the average cost when x equals 50, or in other words, the average cost for the first 50 items. So what do you need to do? You need to do C bar of 50. So all we have to do is plug in 50. I'll put parentheses wherever we plug in, into our average cost function, and then do our computations, and we're going to get $107.50 per item. Okay, that is the average cost to produce 50 items. $107.50 per item. Okay, hopefully that makes sense for what we're going here. So, believe it or not, we could have also substituted in, let's say, another number. So I'm going to do this as an aside because I can see this being very helpful for all of you. So aside, which is below, so not exactly aside. So what if we did C bar of 100 instead, and we did 1,000 over 100 plus 100 minus 0.25 of 100. So I'm doing this on a whim here, so let me just do some calculator action here. So 1,000 divided by 100, which will definitely be 10, plus 100, and then plus 0.25 of 100. Let's just make sure all this is good. So we're going to get 100, so just to be clear, so this is 10 right here, and 0.25 of 100, of course, a quarter of 100 is 25. So we're going to get 135 as our value. So why did I do this as an aside, even though it had nothing to do with this problem? Because if you look at this number here, this is the average cost to produce the first 100 items. So if it cost $107.50 for the first 50 and $135 for the first 100, then what has happened to the cost of the manufacturing process after it left 50 items? It increased. So I'm showing this not because it's this problem, because it proves to you that the cost of manufacturing this item has increased over time. So just a small thing to help you understand the concept altogether. Okay, next question. It says determine the marginal cost. Okay, so we learned that the marginal cost was C prime of x. So C prime of x is going to be equal to the derivative with respect to x of our function 1,000 plus 100x minus 0.25x squared. Okay, what does that look like? Well, the derivative of 1,000 is 0. The derivative of 100x is 100. And then the derivative of this is 2 goes to the front, and you get 0.50, leaving an exponent of x. So this is the marginal cost function. Okay, most students don't really get that in the beginning, so you must do an example to fully understand what that's about. So what if I want to know the marginal cost for x equals 50? We would do C prime of 50, which is going to be 100 minus 0.50 times 50, which is equal to $75. Okay, so what is this saying? This is the cost of producing the 51st item. So if I have 50 items, the 51st item will cost $75. Now, how interesting is that? We found that the average to compute all the items in the first 50 is $107.50. So that means if the 51st item was $75, that means it was decreasing from beginning to finish. So at some point it must have gone back up in order for the average to go up to 135 after you pass 50. So it's very interesting to see. Note, these are all just polynomials that are all over the place that increase and decrease, but that is the concept of a marginal cost in the scope of what we're doing.